Okay, we're up to chapter 13 and gases as we finished up, I think, stoichiometry last time. All right, so let's talk a little bit about substances that do exist as gases under normal conditions. And sort of normal conditions is usually a pressure that refers to 1 atm, which is an atmosphere, and that is, again, a unit of pressure, and 25 degrees Celsius, which is sort of like room temperatures usually, in most cases. Now, under these sort of normal, sort of everyday conditions, ionic compounds typically do not exist as gases, and that's again because they're held together by really strong electrostatic attraction between the positive ion and the negative ion. And essentially, you could kind of heat the heck out of an ionic compound, and it really will not go into the gas phase because of this really strong attraction forces. It will actually just start to melt before it will even try to even go to the gas phase, and it really will not sort of happen because, again, it's held together by pretty much the strongest attraction you could have, which is the electrostatic attraction. Now, when we talk about molecular compounds, which are different than ionic compounds, as we hopefully remember, they are held together by sharing of electrons. Obviously, ionic compounds are held together by the opposite attraction. They are very much different in terms of their sort of states. There are some molecular compounds which are gases kind of right out of the box there, like carbon monoxide, carbon dioxide, hydrogen chloride gas, ammonia, and methane, CH4 there. But a lot of molecular compounds are liquids, are solids at room temperature. One of the main differences, though, is, thank you, that a molecular compound usually can be converted into a gas a lot easier than an ionic compound. And that is because, for example, if we take something like water, water is held together between what is known as hydrogen bonding, and water positive side is the hydrogen, negative side of water is the oxygen, and they actually bond to each other through opposite attraction. This is what is known as an intermolecular force. And that's the force that holds one whole molecule together with another. So, and that's different than if you just took one water molecule by itself. The bond at the hydrogen and oxygen on each side, these are known as what are known as intramolecular forces, as opposed to intermolecular forces. And intramolecular forces are forces that hold one single molecule together. Basically, your kind of covalent bonds, the sharing of electrons that kind of holds that whole just individual molecule together, versus intermolecular forces, which just hold one entire molecule together with another one. And what happens is when we have something like water, the intermolecular force will start to break first. And we know that because it's usually much weaker. Because when we do heat water, we break this bond between the two water molecules first as we start to heat it up. And that allows this guy to go off into the gas phase. That allows this entire molecule to go off into the gas phase. Now, that's different than what would happen here. And we know that that is what happens. We do get water in the gas phase when we do that. If the intramolecular force, the forces over here were actually weaker, when you would heat up water, you would just get everybody falling apart. You get hydrogen gas, oxygen gas form, which obviously doesn't happen if you ever boiled water. You don't do that. But so these bonds here are much stronger. Otherwise, again, when you go heat water, it would basically just everybody would just fall apart into their elements, and obviously that doesn't happen. So the much weaker bond there between the two water molecules being held together breaks first, and again, that's why it's easier in the case of water, for example, to go into the gas phase as opposed to, say, an ionic compound where they're held together with an intramolecular force of electrostatic attraction. So the general rule is the stronger the attraction between molecules, the less likely that you will find those molecules as gases under ordinary conditions. So, what are some substances that we do find as gases under normal conditions? Well, a lot of those diatomic elements that we have talked about previously, hydrogen, nitrogen, chlorine, fluorine, these guys exist as gases under normal conditions. Obviously, something like ozone, which is O3, is also a gas. And then obviously group 8 on the periodic table, which is our helium, neon, argon, krypton, are also gases under normal conditions. Unlike hydrogen, nitrogen, oxygen, which are diatomic, our noble gases are monoatomic, which means they come as ones basically. So if we kind of look at the periodic table, pretty much these guys here are normally gases under normal sort of conditions. So this is also a good time to talk about the difference between a gas and something that is sort of considered a vapor. And typically we use the word gas to recognize a substance that basically is in the gas state under normal conditions, temperatures and pressures. And a vapor, on the other hand, is something that normally is not found in the gas state, but is converted into the gas state uh, under normal temperatures and conditions. So, water is an example of that. When we talk about water in the gas phase, we usually refer to it as water vapor rather than water gas because it just kind of sounds funny as well. But water vapor, again, because water under normal conditions is found as a liquid, but it can be converted into a gas. So if something is referred to as a vapor, it is normally found in a different state under normal conditions. Any questions on that there? So let's talk a little bit about the pressure of a gas. Um, the kind of composition of air, as maybe you're not familiar with, but maybe are. The major component of air is actually nitrogen gas, followed by oxygen gas, and then other gases, depending on sort of what air, where you're breathing that air, I suppose, as to what's in the air. One of the sort of measurable properties of gases is pressure. And when we talk about something in the gas state, we are talking about something that everybody has pretty much at this point broken apart from one another. They have probably the most energy of any state, obviously, solid and liquid. And as they're flying around in the gas state, they are colliding with the container, and that collisions with the container is what basically exerts the pressure that we associate with gases. And obviously, more collisions will result typically in more pressure. Less collisions as they're flying around would result in a lower pressure happening. Now, how do we measure pressure? Well, one of the common ways that we measure pressure is with a barometer. And a classic barometer, which we'll see a picture of in a second, sort of a classic barometer is a pool of mercury. And typically in that mercury is a glass sort of tube. And as the atmospheric pressure sort of exerts on it, the mercury in the tube basically rises. And that's your sort of classic barometer. Most schools have taken those out because they have mercury in it. So we don't really have sort of a classic barometer anymore. We do in the lab have more of an alcohol sort of barometer, I think, that's on the wall. And we'll use actually a digital one, I think, in the experiment today. But some common units of pressure is an atmosphere, which is an ATM, a torr, which is named after the guy who invented the barometer, and an mmHg. mmHg is millimeters of mercury, and that is because on these barometers, there is usually a ruler, and you can take measurements of where the height of the mercury is on the tube using that ruler, and a lot of times it's in inches, centimeters, or sometimes millimeters of mercury is basically what you are measuring. So a couple of really important conversions are these. You do need to know these. These are, I would say, are definitely the big three sort of pressure units that you most often come across in chemistry: atmospheres, millimeters of mercury, and torr. 1 atmosphere is equal to 760 millimeters of mercury and 760 torr. So that 760 number is basically your conversion factor. So if you have atmospheres and you want either millimeters of mercury or torr, you are going to multiply by the 760. And vice versa, if you got millimeters of mercury or torr and you want atmospheres, you're going to divide by the 760 there. So again, that 760 is sort of an important sort of number. 1 millimeter of mercury is equal to 1 torr, so the conversion between those two units is pretty simple. It's basically just change the units. The number stays the same. It's a 1-to-1 relationship in terms of those units. So definitely atmospheres, millimeters, mercury, and torr are three units that you very commonly will see a lot in chemistry. Here is an actual nicer picture of a barometer, and again, you can see there's a pool of mercury, atmospheric pressure, mercury goes up. And like I said before, typically on the glass there's some type of ruler where you can make that measurement. As you can see in the picture, and as we might have talked about in a previous chapter, mercury is one of the unusual substances that its meniscus actually goes in the opposite direction. It's not a U meniscus, but it kind of goes upwards. So if you ever were to read a mercury barometer, there's a bad drawing there, you will actually read from the top of the meniscus as it kind of goes upwards. Unusual, not a U meniscus. Now, some other units that we really don't come across too much in here, but you should be familiar with. A Pascal or a kilopascal, 101,000 pascals is an atmosphere, 101.325 kilopascals. Also, 14.7 psi, pounds per square inch, is 1 atmosphere. Yeah. So that is pounds per square inch. And also, one very rarely seen a lot, but 1.01 bar is equal to 1 atmosphere. So a bar is another common unit of pressure that I can come across, especially in old tables and stuff like that, in books and stuff. Sometimes people will use bar for pressure rather than atmospheres. And again, obviously PSI, where we kind of fill up our tires and stuff like that, is a common unit. All right, so we're going to talk about a bunch of different sort of gas laws. And when we talk about gas laws, there's some variables that we commonly come across, and that is pressure, volume, and temperature. Those are the three sort of variables that we come across. And in certain cases, maybe one of these are held constant, and other cases, maybe a couple are held constant. So the first sort of gas law we're going to talk about is Boyles Law. And what Boyle did was he looked at the relationship between pressure and volume, and he held temperature constant in this case. So he looked at the pressure and volume relationship with constant temperature in this particular case. And what he noticed was an interesting sort of relationship, which is as the volume decreased, the pressure would increase. So if you just think about it a little bit logically here, if I have a very small volume of gas, and I have my gas molecules basically in there, there's going to be a very good chance of a lot of collisions happening because they don't have to travel very far to collide because there's not a very big volume. So that's going to increase the number of collisions, and that will increase the pressure in this case. And vice versa, as the volume increases, the pressure will decrease. So if we have a much larger sort of volume, it's going to take longer for our gas molecules basically to collide. And that's going to actually have a lower amount of collisions. And we actually will see the pressure basically come down. So the relationship with Boyle's law basically is one goes up, the other comes down. So inversely proportional to each other. Also, a very interesting thing that happens with Boyle's Law is if you do an experiment where you take a bunch of pressure and volume relationships or measurements and you keep the temperature constant, you can take every pressure volume combination you get and it will equal the same number. So if you take those pressure and volume measurements that you do and you multiply them together, they will always equal the same number. And that's sometimes referred to as a proportionality constant. And that's what the little k sort of stands for there. And because of that relationship, that if you take every pressure times volume relationship and it equals a constant number, it allows us really to get to Boyle's Law as we kind of know it, which is P1 times V1 equals P2 times V2. Once again, this is at constant temperature. And as I mentioned before, pressure goes up, volume goes down, pressure goes down, volume goes up. So that opposite, again, relationship. Now, in terms of units here, units really do not matter as long as they are the same units. So you can use any pressure unit you want in this formula as long as both P's are the same units. And same thing with volume. You can use any volume measurement you want as long as both volumes on each side are the same unit. So that's the only sort of thing you have to be careful of. That if you have two pressure values given to you, you need to make sure they're the same unit. Or if you have two volume values given to you, you need to make sure they're in the same unit. And this is sort of like a before and after type of situation that you could calculate. Any questions on that there? All right, so let's take a look here. Here's our graph of a Boyle's Law relationship. And what we see is, again, larger volume, smaller pressure, smaller volume, larger pressure happening here in this situation. All right, so why don't you give it a go here? An inflated balloon has a volume of 0.55 liters at sea level at 1 atmosphere. It rises to 6.5 kilometers where the pressure is 0.4. Human temperature remains constant. What is the final volume? A moment or so. Let's see what you end up with. Okay, let's take a look. So I say definitely in sort of gas law type problems, a really good thing to do is just kind of pull out the information and label what it is. So obviously here we have a volume that is 0.55 liters. We have 1 atmosphere, which is a pressure. 6.5 kilometers is useless information in terms of this. We have a pressure 0.4 atmospheres, and we are looking for a volume. So if you kind of do that, you could almost see, obviously we only have a choice of one gas law at this point, which is Boyle's Law, and you can kind of hopefully see it there. You usually will kind of just label the first things in the problem, the ones, and the second ones, the twos. It really doesn't matter. We are going to use P1 V1 equals P2 V2. In this particular case, we are going to solve for V2. When you move across the equal sign, it ends up in the opposite location, which means you need to divide that to the other side. And that's going to give you V2 is P1 V1 P2. Here, both of our pressures are both the same units, so we're good to go on that. Our volume's in liters, and what that just means is when we solve for it, we'll be in liters when it's all said and done. So P1 here is 1 atmosphere. V1 is 0.55 liters divided by our P2, which is 0.4 atmospheres. In this case, our atmospheres are going to cancel, and that's going to give us 0.55 divided by 0.4, and we'll go with 1.4 liters in this particular case. Any questions on that one? Now here we do see the relationship that we talked about. So this is Boyle's Law relationship. And what we see here is our pressure went down. That means our volume should go up. And it did. It went from 0.55 to 1.4. So again, we do see the Boyles Law relationship there that we would expect in this particular case. Any questions on that there? The next relationships we're going to talk about is Charles and Guy Lussac's law. And they looked at a couple of different sort of relationships. Charles looked at volume and temperature relationship, and he held pressure constant. Guy Lussac sort of looked at pressure and temperature and held constant volume in this case. And let's take a look at sort of what we should expect to happen in each of these cases. So we'll take a look over here at Guy Lussac's law first. So if I have a container where I have basically a fixed volume and I got gas molecules in there, what's going to happen in this particular case is as I increase the temperature, my gas molecules should definitely start to fly around a lot faster. And that's because, again, they will have more energy as you increase temperature. And because they're going to fly around a lot faster in that volume that's basically fixed, that is going to increase the number of collisions that should occur. And because of that, what we would see in terms of the pressure is we would expect the pressure to also increase as well because of the gas molecules flying around faster, causing more collisions and increasing the pressure. Opposite is true. If you lower the temperature, your gas molecules are now going to fly around slower, dramatically drawn here, slowly moving. And as they're moving around slower, that's going to lead to less collisions going to happen in that fixed volume. And because we'll have less collisions in the fixed volume, we would expect to see our pressure goes down. So in sort of the Guy-Lussac relationship, where we have a fixed or rigid volume that's not going to move, when you increase the temperature, you do expect to see the pressure to go up with it because, again, you're ultimately increasing the number of collisions that's happening. When you decrease the temperature, you expect the pressure to drop because, again, you're lowering the number of collisions that are occurring. Now, if we look at the Charles law relationship, which is volume and temperature, and keeping the pressure constant, we see something a little bit different, which is if we have a container where this volume is movable, so like a movable sort of piston, if you will, and we have these gas molecules in there. Because this is at constant volume over here, this is at constant pressure. So what happens in this particular case is if we increase the temperature, we are going to see exactly the same thing as we see on the other side, which is our gas molecules should now start to move a lot faster. They're going to be flying around a lot faster in there because of the increase in temperature. Now, the difference, though, between on the left here and on the right is on the left here, we want constant pressure. So we know that what we just saw on the right there was if our volume stays fixed and we increase that temperature, we should expect basically the pressure to start to increase. But in order to keep it at a constant pressure, what happens in the Charles law situation is the volume actually adjusts and the volume goes up. So now even though our gas molecules are flying around faster, we're going to give them a lot more room to fly around in. And because of that, that keeps the number of collisions relatively constant. And that is how we maintain, in this situation, constant pressure. So as you increase the temperature in a Charles law situation, you would expect the volume to adjust to allow it to maintain constant pressure. Because everybody's, again, just a lot more room to fly around in and ultimately keep the number of collisions that are happening basically being constant. Any questions on that? Now, what happens in the opposite situation? And the opposite situation is if we lower the temperature, just like we saw over here, we would expect our gas molecules to start to fly around slower and move slower, which if the volume stays constant, would result in the pressure dropping. So again, here to keep the pressure constant, what happens in our Charles Law situation is our volume decreases. So our volume goes down. And now because our volume is decreased and our gas molecules are moving slower, they don't have as far to go to cause collisions. So that helps maintain the same number of collisions. And that is how we maintain, again, constant pressure. So in the Charles Law situation, the way it's able to maintain that constant pressure is the volume adjusts accordingly to what you're doing. So temperature goes up, you increase the volume, and vice versa. If you lower the temperature, the volume will get smaller as well to maintain that constant number of collisions and the constant pressure. In the Lussac situation, the volume is fixed, which means as soon as you increase that temperature, you're going to have more collisions because it's going to hit the container and so forth a lot more, and we're going to see an increase in pressure. And again, because of the fixed volume, if you lower the temperature, you will end up with a lower pressure. Any question on the relationships up in here? Now, we'll come back to this in a second here. If we take a look at a graph of sort of a Charles Law situation, and if you look at a graph of volume versus temperature for any gas you like, you've got helium, methane, water vapor, and so forth. If you follow each of these straight lines back to the temperature graph or temperature axis, they will all hit at exactly the same point. So they will all hit at this point here, which is minus 273.15 degrees Celsius. So that number should look familiar to you. That is the number we use basically to do what? Convert Celsius into Kelvin. And Kelvin recognizes its relationship because if we convert this into Kelvin at 273.15, gives us 0 Kelvin. And he called that absolute zero, basically. And the funness of that is pretty much if you're doing a gas law and you're doing some type of gas calculation, your temperature needs to be in Kelvin. So it absolutely 100%, if there's any temperature in any gas, it needs to be put into Kelvin. And then obviously here we know how to convert it, which is adding our 273.15. So even on problems where people sometimes feel maybe I don't need to convert it into Kelvin because they give me the temperature in Celsius and then they ask for the temperature in Celsius. The answer is you do need to convert it to Kelvin. So as soon as you go into the gas law, you got to convert it. So if they give you the temperature in Celsius, you got to convert it to Kelvin, go into the gas law, and then convert it from Kelvin back to Celsius as well. So always into the gas law, it's got to be in Kelvin. You got to add that 273.15 to it, since they like the 0.15 here, to convert it into Kelvin. Any questions on that there? All right. So again, let's talk a little bit about each of the sort of gas law. This is Charles' law here. And Charles' law is V1 over T1 equals V2 over T2. Once again, as we just talked about, Kelvin. It needs to be in any gas law. The temperature, here the volume doesn't matter. It could be any unit you want as long as they are both the same. And sort of Lussac's law is P1 over T1 equals P2 over T2. Once again, this is that constant volume. And as we saw before, pressure goes up as the temperature goes up. Pressure goes down as the temperature goes down. And this is at constant pressure over here. And as we saw there, volume goes up, temperature goes up, volume goes down, temperature goes down. So again, those are the relationships here. And just like the other gas laws, temperature here, also Kelvin gonna need to be. All right, so we got Boyles Law, which deals with pressure and volume. We got Charles and Lussac's Law, which deals with temperature, pressure, and temperature. Any questions on those there? And obviously, you need to know these gas laws here. There it is. All right, so let's try one here. In an experiment, 452 milliliters of a gas is used in a light bulb. It's heated from 22 degrees Celsius to 187 degrees Celsius. What is the final volume? So take a moment there and see what you end up with. Okay, let's take a look. And again, if we pull out the information, we got a volume of 452 milliliters. We have a temperature of 22 degrees Celsius, another temperature of 187, and we are looking for a volume. So again, just kind of pulling out the information, you should hopefully see which gas law looks good. There's no pressure, so Boyles is no good. No pressure. Lussac is no good. So right here would be probably your only choice, as it has volumes and temperatures. Once again, you can label the first ones the ones and these guys the twos. As we just talked about, probably most important for any gas one is the temperature needs to be converted to Kelvin, which it is not here. So we do need to add a 273.15 to each of these. And that's going to give us some temperatures here, 22 plus 273.15. Going to be a 295.15 Kelvin and a 187 plus a 273.15, a 460 it looks like, 0.15 Kelvin. Now that we have that, we can take our gas law, our V1, T1 equals V2, T2. And once again, we are solving for this guy. So when we move somebody across the equal sign, they end up in the opposite location. T2 is on the bottom. It will end up on top when you move it across. And that will be V1 T2 divided by T1 is equal to V2 in this particular case. Popping in our numbers, the right numbers in the right location, we're going to end up with 452 milliliters. Our T2, 460.15 Kelvin, divided by our T1, which is 295.15 Kelvin. Once again, Kelvin is going to cancel. That means that our units here will be milliliters. And we got 460.15 times 452 divided by 295.15. Going to get us a, call it 705 milliliters in this particular case. Any questions on the calculation? Once again, we should be able to see our relationship. Our temperature in this case went up. And since this is Charles' Law relationship, we should expect our volume to go up as well. And our volume went from 452 to 705. So it did increase as in this case. Again, that is how it maintains the constant pressure in this example. Any questions on that there? The next sort of gas law we're going to talk about is our friend Avogadro. And Avogadro had a number, and he also had a gas law. So when we think about Avogadro, we should think about Avogadro's number, which is equal to a mole, right? And not surprisingly, his gas law does involve moles. And in gas laws, a mole of something is basically abbreviated with an N. So when you see an N in a gas law, it represents the moles. And basically, Avogadro's law is V1 over N1 is equal to V2 over N2. And volume here is the V's. It could be any unit you want. And once again, N here are the moles of the gases, basically, in this case. And this gas law is actually under two conditions. It's actually under constant pressure and temperature. So under constant pressure and temperature is when basically Avogadro's law comes into play. And basically the idea here is the volume related to the number of moles are directly proportional. got two volume moles of gas happening. Now, one of the ways that you can use Avogadro's law is like any other gas law, you could plug and chug into obviously the formula there, and you could solve for, whatever is missing. A sort of byproduct of Avogadro's law is that as the volume and moles sort of increase sort of directly to each other, the volume doubles, so does the moles. The relationship is you could actually use Avogadro's law in stoichiometry. And one of the ways that if you do have this situation of constant temperature and pressure, and you're doing some type of stoichiometry problem, it actually allows you to actually not use a gas law to solve. I'm going to talk later in this chapter about the stoichiometry, use the gas law. But if you happen to be on temperature and pressure, you can basically use Avogadro's sort of law and relationship like we do stoichiometry, which is, for example, in this equation, we would normally say if we were doing stoichiometry, 1 mole of N2 would give you 2 moles of NH3. That's sort of the mole-to-mole relationship. Because this is under pressure, constant pressure and temperature, we could actually use a sort of volume relationship and say 1 liter of N2 would produce 2 liters of NH3. So instead of a mole to mole relationship, we could actually do a volume to volume relationship. So for example, if we started with, in an example, say 3 liters of N2, and we want to know how many liters of NH3 would we produce, we could actually just approach it like a stoichiometry problem involving volumes. We would use our 3 liters of N2, go to the equation like we did here, and find our relationship, which is 1 liter of N2 gives us 2 liters of NH3. The liters of N2 would cancel, and we would expect to produce 6 liters of NH3. So sort of a benefit of law other than the other gas law is we actually have a stoichiometry problem that is under conditions, and the only way you can use this relationship is it has to be those conditions there, constant temperature and pressure. You could do kind of a volume to volume relationship rather than a mole to mole relationship, and it can save you some time actually without having to use like a gas law to kind of figure it out. And you could kind of just do that as well. Any questions out there? That's sort of a byproduct of Avogadro relationship. We will see stoichiometry a little later on where you can't really do that. You got to kind of use a gas law somewhere along the way to sort of solve it. But under these conditions, you could almost bypass it and kind of do a very simple sort of calculation. All right, then let's talk about the ideal gas law. If we take pretty much all the other gas laws and put them together, we get the granddaddy of them all, which is the ideal gas law, and that is PV equals nRT. One of the first differences that you probably can recognize when you look at the ideal gas law is this. It is like a one and done situation. And what I mean by that is all the other gas laws, there's like 2 pressures, 2 temperatures, 2 volumes, kind of like a before and after. Here you're just going to have one piece of information for everybody. I will also say that the ideal gas law is the most restrictive in terms of the units that you have to use when you use it. So when we look at PV equals nRT, the pressure when you use this equation has to be in units of atmospheres. The volume has to be in units of liters when you use this equation. The N, which is moles, should be in moles. And no surprise here, our temperature needs to be in Kelvin. The reason that all of those guys has to be in that specific units is because of R, which is the gas constant. And R has a value of 0.08206. Some books will round this to 0.0821. Some books will kind of round it to that number. But the units that go with R are liters times atmosphere divided by Kelvin times mole. So that is why all these other guys, for everything to properly cancel out, has to be in those units. So you want to make sure that everybody is in those units. I will say that common conversions that you need to use to get everything into are definitely grams to moles conversion that we've talked about, which again is our molar mass, is a very common conversion. And I would say very commonly, your volume is oftentimes given to you in milliliters. So milliliters to liters conversion is also a very common sort of conversion that is used. 1,000 milliliters equals 1 liter. So I would say, again, those are very common conversions. The temperature also super common because it always needs to be in Kelvin. Now, you should also think about the R value or the gas constant as a value that you always have. So it is a constant number. You always have it. I will tell you that pretty much no problem ever mentions R. So when you go through the problem, they will never mention R, the gas constant. They just assume that you know that number and that you know you have it available to you. So if you're going through a problem, you got like a pressure, a volume, you got a temperature and you're looking for moles, and that's all you got, you need to know, oh, I also have R always sort of available to me. And again, very rarely ever mentioned in any type of problem when you look at it. Any questions on that there? Let's talk about a couple of other important sort of conditions and how we get to that value of R. The first condition is, let's talk about STP. And when somebody says STP, they are talking about standard temperature and pressure. And when they do say STP, they are actually giving you a value for each of those. So if they say STP, that means that you should be using the temperature of 273.15 Kelvin and a pressure of 1 atmosphere, or equivalent basically, which would be 760 torr or so forth. So when it says in a problem at STP, you actually have both of those values given to you, and those are the values you should use for pressure and temperature. It has to be both of those values for it to be at STP. So the temperature has to be at 273.15 Kelvin, and the pressure has to be 1 atmosphere for them to be at STP conditions. Now, one of the nice things about STP conditions is if you happen to be at STP conditions, there is a nice conversion factor that you could use that will allow you not to have to use perhaps the ideal gas law. So you can kind of bypass the ideal gas law if you're at STP. And that is this one that we could use in our experiment today. 1 mole of any gas is equal to 22.414 liters. This has to be at STP. So you can only use, if you are at STP, this relationship. If you are not at STP, you use the relationship to the side, and you can use the ideal gas law. So if you are at STP, you can bypass the ideal gas law, and again, just use that conversion. The ideal gas law can be used for any conditions, STP conditions, non-STP conditions. You can always use the ideal gas law. But again, this conversion, the 1 mole 22.414, absolutely has to be a STP condition. By the way, that is how we get the value of R. If you put in and solve the ideal gas law for R, you get basically our value of our gas constant, the 0.08206 number there. Liter atmosphere times Kelvin. That's where that comes from. Any questions? All right, why don't we try one here? Calculate pressure in atmospheres exerted by 1.82 moles of SF6 gas in a steel vessel with a volume of 5.43 liters and 69.5 degrees Celsius. We're looking for a pressure. We have moles of 1.82. We have a volume of 5.43 liters, and we have a temperature of 69.5 degrees Celsius. So again, obviously here we have just one of everything. So that pretty much eliminates all the other gas laws that we learned up to that point. That leaves us really just the ideal gas law that is available to us. You could kind of maybe almost see the ideal gas law there. A couple things, as I mentioned earlier, usually never mentioned in there is the value of R, which again is just a number you got to know you have available to you. And now we just want to make sure unit-wise we're good to go into our equation. Obviously, moles are good. Liters is the right unit for our volume, so we don't have to do any conversions there. Temperature, like normal, we do need to do a conversion, so we'll add our 273.15, and we will end up with, if I can turn my calculator on here, 69.5. Looks like 342.65, I think. 342.65 Kelvin. Taking our ideal gas law here, we're going to solve for P. We're going to bring that to the other side by dividing it, so it's going to end up in the bottom location. And it's going to give us nRT divided by V. Putting in our numbers here, our N is 1.82 moles. Our R is 0.08206 liters atmosphere Kelvin mole. Our temperature 342.65 Kelvin, all divided by our volume of 5.43 liters. Moles will cancel, Kelvin will cancel, liters will cancel. Gonna leave us just atmospheres left over in terms of the units. And popping those numbers in, multiplying the top. And then hitting equals and dividing by the bottom. About a 9.42 atmospheres here. Any questions on that one there? On the bottom, where it's scratched right here. Yeah, that's Kelvin times moles on the bottom. Yeah. Other questions? Okay, let's take a look at another one here. Let's see. All right, so calculate the pressure exerted by 32.5 grams of SF6 gas in a volume of 252 milliliters and a temperature of 45.5, sulfur 3207, and fluorine 19 from the periodic table. 32.5 grams, which we can get moles from. We have a volume of 252 milliliters and a temperature of 45.5 degrees Celsius. Once again, we always have R available to us. So here again, we're going to use our ideal gas law. Our PV equals nRT is the one that really fits. And again, we're going to rearrange it by dividing the volume to the other side. We do got to watch out for some units here. So we do need to convert this into liters. So 252 milliliters, 1,000 milliliters is a liter, going to give us 0.252 liters. We also, like normal, need to convert our temperature into Kelvin. So if we do that, 45.5 plus 273.15, 318.65. And also a very common conversion, we do need to convert our grams into moles. So again, that's going to require you to go to the periodic table there, get the molar mass of SF6, so that's 3207 grams per mole, plus 6 times 19 grams per mole. That's going to get us, looks like 146.07. grams per mole. Remember, we're going to use that as a conversion factor to convert our grams into moles. So we'll divide by 146.07 grams per mole. Now we got, we'll call it 0.2225 moles. So now that we got everybody in the right units, we're ready to go into our formula here. So our pressure will equal our moles, 0.225, times our R, 0.08206 liters atmosphere, Kelvin mole. And our temperature, 318.65, all divided by our volume here, which was 0.252 liters. Moles will cancel, Kelvin will cancel, liters will cancel, going to leave us once again atmospheres as the only unit left, and that's going to get us here. Looks like 23.1 atmospheres here. A huge amount of pressure. There's any questions on the calculation? So again, this is very common conversions to just do grams to moles, like I said before, milliliters to liters. Obviously, temperature into Kelvin are very common sort of ideal gas law sort of conversions. Any questions on that? Ideal gas law. All right, then let's take a look at another really important sort of gas law, which takes a look at differences in pressure, volume, and temperature. So this gas law will basically look at variations in all three variables. And we really get to it by looking at the ideal gas law and solving for the ideal gas law and the R value for each of them for two different conditions. And because R is a constant, we could set them together and we get sort of this relationship here, which is basically two ideal gas laws set together through R. And in most cases, the number of moles doesn't really change. So this gives us this gas law here, which is typically what it looks like. P1 V1 over T1 equals P2 V2 over T2. And this is what is sometimes referred to as the combined gas law. Pressure in this formula doesn't matter as long as they're both the same unit of pressure. Volume doesn't matter as long as they're the same unit of volume. Temperature does matter like normal, needs to be in Kelvin. Now, obviously, you could use this formula just like any other and solve for whatever's missing if you have, obviously, the other stuff given to you. Why is this one really the best one? If you want to invest your time into, this is the best one to remember, to be honest with you. So let's talk about why this one here to finish up on is the best one. Now, if you take the combined gas law, the P1, V1, and even if you want to leave the moles in there, N1 and T1 equals P2, V2, N2, and T2. So let's say you come across a problem and it doesn't mention anything about moles or grams, doesn't mention anything about temperature, or it tells you it's constant. All you have to do is come to this formula and scratch those things out. And now you are left with our good friend, Boyles Law. If you take this formula here, P1, V1, N1, T1 equals P2, V2, N2, T2, and you come across a problem where, again, they don't mention anything about moles or grams, they don't mention anything about pressure, you just, scratch those off on both sides, and you are now left with our friend Charles' Law. If you take this one here, the combined gas law, and you come across a problem that doesn't mention anything about volume or moles, and you scratch that off on both sides. And now you have Guy-Lussac's law. You take our combined gas law here, and you come across a problem where it mentions nothing about moles or moles or, I'm gonna spit that out right, pressure or temperature. That's what I'm trying to spit out there. So if it mentions nothing about pressure or temperature, or you're told they're held constant, you scratch out pressure and temperature on both sides. And now you have Avogadro's law. Heck, even if you can't remember the ideal gas law, and you take P1, V1, N1, T1 equals P2, V2, N2, T2, and you look at all your information, and all you have is like pressure, volume, moles, and temperature, and you only have one of each, and you know that this equals R, you can scratch that out, and now you have basically the version of the ideal gas law right there as well. So if you want, my advice would be, since you have to memorize all these, I would invest your time in remembering this formula. And frankly, just scratch out what's constant, what's not given to you. And if you don't want to worry about rearranging this one, just remember the ideal gas law with it. And you'll pretty much be able to have any gas law you need from those two, or even really those just one by itself. You could get pretty much all of it there. Any question on there? So obviously you can use the combined gas law like normal, plug and chug into it. But again, remembering that formula, crossing out what's not given to you or constant, will pretty much put you in place to use the right formula for any of the other gases you need to do, or gas problems you need to do. Any questions on that there?